that was an exhilarating time and one that I'll always remember. The briefing Joe asked me to give today was not the one that I gave that day. It was the one that a gentleman by the name of Morris Jenkins gave, who was one of my bosses at the time, on, as Joe said, software considerations and constraints, excuse me, relative to the mission. The one I gave that day was on the return to Earth abort analysis and planning, and if time permits, I might try to sneak a chart or two at the end of this from my briefing. To make this as a faithful a recreation as possible, I'll try to, or I'll at least attempt to use present and future tenses instead of slipping into the past tense thing, which is difficult to do. And also, as you may have already noticed, because Morris was an Englishman, that again, to further recreate accurately that briefing is why I'm using a British accent today instead of my natural Texas drawl, and I'm going to continue to do that. If I slip back into my natural one, just yell. Could I have the first chart, please? In terms of the overall mission software considerations and strategies, as this chart shows, obviously they were driven by a combination of crew safety and mission success. But the other point was that the strategy was to really have a partnership between the onboard and the ground. It was not just going to be the onboard show for various reasons. As the first bullet indicates, of course, the onboard software capability did have plenty of features that ensured crew safety as well as enhanced mission success. And helping that capability was the ability that it had to accept information from the ground, uplink from the ground during the mission. The ground capability was actually prime and essential in certain cases. One of the previous speakers mentioned that much of the navigation during the mission was prime from the ground, as well as a lot of the maneuver targeting. And likewise, the ground provided enhancement to mission success, as well as served as a provider of various peripheral data like AC and LOS times, predicted lighting conditions, and so on. And then another part of the strategy was, when appropriate, to use combined onboard and ground software solutions when so combining would enhance crew safety or provide a more optimum resulting mission plan or trajectory. Have the next chart, please. Elaborating a little bit on the onboard's capability relative to crew safety, the plan is to, I'll try to use present tense, the plan is for the onboard to have an independent capability to return to cover the obvious case of loss of communications from the ground. When the ground cannot provide return to Earth targeting, maneuver targeting, and navigation support, then the onboard will have an independent capability to provide that. Now, in actuality, what happened, even that turned out to be somewhat of a combination of onboard and ground, because we ended up using what was called advanced block updates, where the ground would send it return to Earth solutions for some future time, so that you lost comm between then and that future time. You would have a block update maneuver to execute. As I mentioned, the onboard will have the capability to accept ground updates. It will provide compatibility of software between the primary guidance system and the LIM and the abort guidance system. Example being the compatibility of targeting for LIM ascent. It will provide a double check on relative state for rendezvous, where the limb is determining the relative state with its radar. The CSM is determining the relative state with sextant tracking of the limb. Also, the capability will exist for the limb to direct a CSM active rendezvous. The solution would be computed on board the limb and voiced over to the CSM, where the CSM pilot would punch it into the DSKY, the maneuver targeting information. And also, the software will provide meaningful crew checks in terms of the input and output data, and display something in a format that has some physical meaning to the crew wherever possible. In terms of mission success, of course, the onboard software will be providing the necessary steering or thrusting guidance programs. For translunar injection, though the Saturn will be primed for translunar injection, be providing the steering using its iterative guidance for that maneuver. The CSM CMC computer will have backup capability to steer translunar injection if for some reason there's a loss of capability for the Saturn to guide through translunar injection. And as I mentioned there, the onboard will have the ability to accept alternate targeting from the ground to provide more optimum solutions. Next chart, please. The basic onboard GNN software capability is described on these charts. There are 4 classes of programs proposed for onboard. The navigation class, where you have observations, nav observations fed into a trajectory determination processor, outputting, which it would then output, after it does its thing, the current smooth position and velocity determination. Answering the question, where are we? To answer the question, where will we be, we have the class called dead reckoning. That was one of Morris's favorite terms. I call it trajectory prediction. He calls it dead reckoning. But it involves taking an ephemeris or a state vector input into a trajectory prediction processor and outputting the best estimate of future position and velocity. And you also had the pre-thrust programs, which would essentially determine the change of course required, coming out with the target objectives for the thrust programs. This is where the targeting was set up and configured to tell the steering thrust programs what to steer to. Then you did finally have for the purpose of maneuver control, you had the thrust programs themselves, which included the steering equations to achieve the desired target conditions, including the achievement of the desired cutoff conditions. Elaborating on that just a second, the trajectory determination processor, the basic component there was is proposed to be a Kalman filter, which will filter out noise in be a mathematical formulation to filter out noise in the measurement data, as well as provide the capability to solve for uncertainties in the various dynamic models, primarily the gravity model. Trajectory prediction processor will feature the Inky method of numerical integration. For you numerical integration buffs, you all know what the Inky method is. It's where you do the numerical integration instead of in the equations of motion in totality. You just numerically integrate the deltas from a base closed form two-body solution. So that you our studies up to this time show that's will provide a superior accuracy or superior speed, same accuracy if you want to take larger steps. The pre-thrust programs, as I mentioned, set up the targeting. They determine the initial thrust command attitude and determine the preferred platform alignment. The thrust programs include the MIT's cross-product steering, which is a simple but reliable steering law, which essentially requires the cycle-to-cycle determination of a closed form velocity to be gained, which is kept, that velocity gained vector is kept inertially fixed, and the steering law shrinks its values as you go through the burn. The e-guidance is a more sophisticated guidance law for when you're trying to control more parameters, such as be required for the limb ascent and descent. Then you got the local vertical coordinate or external delta V steering law where you're actually thrusting along local horizontal or out of plane coordinates. Next chart, please. Because of the capacity limitations in the onboard computer and the schedule limitations, how much schedule time we've got to implement the requirements in the onboard computer, there will be significant omissions that we will not be able to get into the onboard computer. The self-checking will be restricted. The logic to avoid gimbal lock will not be included. There will be no concentric sequence logic automated in the CMC, as I mentioned earlier, for the CSM active rendezvous. They have to get that maneuver targeting and planning from the limb or the ground. There'll be no flight plan prediction or optimization capability, no point return back to Earth. It will have return to Earth capability, but no ability to return to a specific point on the Earth. And as I said, there will be no sophisticated iterative steerings like the Marshall guidance for translunar injection. Instead, the more simple cross-product steering will be used. Next slide, please. As regards the ground, supplementary and backup functions, many, if not most, of the target determinations will be done on the ground and uplinked. They will also provide pilot monitoring information for manual maneuvers, and they will provide, especially for contingency situations, a much more extensive flight planning, optimization, real-time mission planning function. And it will also provide an umpiring function between the pings and AGs, especially as regards range rate information to assist the limb in ascent switchover monitoring, navigation, and the ever-present dead reckoning down here. Next chart, please. At this point in Morris's presentation, he went into about an hour-and-a-half discussion of the various targeting techniques to be used, and I've just selected 3 or 4 of them to give you a sampling. Morris was a targeting junkie, and he loved it, and he taught me to love it also. Type 1 targeting was for translunar injection, and this was to target the translunar steering for if the CSM was going to be doing it instead of the Saturn. So it had to be a very simple closed form way of computing a velocity be gained. So what you did, from the pre-flight plan that Pete was talking about, you'd pick off near the Saturn cutoff vector, you'd pick off a state vector, determine a conic ellipse, pick off a position vector from that with the energy of the ellipse. And by the way, Pete's depiction of the ellipse was much more accurate than Morris's. Morris showed it a little short on the semi-major axis. It really went way out like that, like Pete showed. But you, with the position vector and the energy of this ellipse, that together with a position vector in real time, somewhere in the vicinity of the translunar injection, is all you need to define that conic, and therefore define a velocity gained in a cyclical sense to supply the velocity gain to the cross-product steering. The targeting type 1 also was used for lunar orbit insertion, with the only additional wrinkle that the target position was constrained to be the same length as the current position, so that you were forcing it to burn into a circular orbit. Next chart, please. The type 2 targeting was used for the translunar mid-courses. Again, they were conic-based. This is a little too complicated because I'm about to run out of time. But you essentially take the pre-flight computed translunar trajectory. Note where it punctures or pierces the lunar sphere of influence at time 2 or at point 2. Now you're on in real time, you're on a dispersed trajectory at time or point T1. You precision integrate where you're going to end up at the same time as T2, call that T3. You compute a conic trajectory between T1 and T3 at the same delta time as between T1 and T2. You then compute another conic trajectory between T1 and T2 to compute the VG, apply it to precision trajectory, and voila, you hit that point if all goes well. Also, I'd like to put one longstanding myth to rest once and for all, that when we did fly the actual missions and punctured the sphere of influence, there was not an audible pop. It was a low hiss. And so the targeting type 2 is also used with a little different wrinkle for the second and third mid-course corrections inside the lunar sphere of influence approaching the moon. I'm not going to have time to go into the details of that. Next chart, please. And targeting type 3 is even more interesting, and because I won't even have time to begin here, but essentially, again, it's conic-based, but here you have the conic centered both at the Earth to consider, as well as the conic at the moon, hyperbola here, ellipse here. You iterate the two until you match them up at the sphere of influence in terms of the energy and position, and then once you get a match on the conics, then you go through the same procedure with precision, backtracking precision back to the lunar sphere of influence, forward until you match at the sphere of influence. And the last chart, backup number 1. I'm going to sneak in one from my pitch. No, go to the next one, backup number 1. There we go. This is one of the most fun things I ever did. It involved doing return to Earth board analysis from the family of trajectories resulting from a premature LOI shutdown. In other words, if you're burning into lunar orbit and you had to be able to recover from a premature shutdown at any time in the burn, you ended up having to analyze this is a trajectory analyst's dream, by the way. You ended up having to analyze a whole family of trajectories ranging from escape hyperbolas to ellipses to circular orbits to even these weird unstable ones which start out retrograde relative to the moon, come down and change, come back posigrade, coupled with the fact you were trying to, you had nearly an infinite number of maneuver possibilities to play with to figure out how to best recover from both time critical and non-time critical situations. That was fun. And that concludes my talk. Any questions?
We have one question here.
Yes.
Was there similar analysis to the one Ron just showed for the translunar injection burn?
Yes, there was. You get a similar family there, and also for the trans-Earth injection burn, you get a similar family. The one for TLI had interesting properties, somewhat different from the lunar ones, but they were interesting also.
Thank you very much, Ron. Our next speaker will be Doug Broom, who was in the Apollo Spacecraft Program Office in 1966 and who is now at NASA headquarters in the Office of Space Science and Applications, and he will discuss the communication systems which we used. Doug?
The key word was that I'm in NASA headquarters. That's why the 10 key charts I needed today are missing. Things haven't changed much since I worked here. Owen, the first time Owen Maynard, the elderly gentleman here, am I right? The first time that he gave the presentation on constraints was interesting. He had an overlay of the moon, and he would flip an overlay for each set of constraints. He'd flip an overlay that blacked in part of the moon. And he got down to his last constraint, and he flipped it over, and the screen was entirely black. And he says, "Gentlemen, we cannot go to the moon." Okay. So he's too old to remember that sort of thing. But Owen and I are related. He's my grandfather. Since I'm from headquarters, I'll take the opportunity to give you a commercial. I'm also the program manager for the Hubble Space Telescope. And if God will quiet the sun and Aaron Cohen will give us an STS in March, we're going to put it in orbit. And it'll be the greatest thing we've done since we landed on the moon. How's that? Okay, I'm going to have to play with the charts a little bit since they're not the ones I was looking for, but communications with a spacecraft is a lot like your relationship with your mother. You know, your mother never wants to let go of control, whereas you always know that you can handle any problem that comes into your life and you don't need control from your mother. So flight crews are pretty independent. They think they can handle any emergency, but the ground never wants to let them out of sight, out of mind, out of control. So that leads to a problem with communications. Okay, and the thing that we had multiple problems going. One was that particular problem. That particular problem was manifested because in the fact that there were a large suite of things that already existed, and we were stuck with trying to live with what we had and at the same time minimize power and weight requirements on a spacecraft. So we'd finished the Mercury program, started the Gemini program, and everything in those programs was done at HF, VHF, or UHF, none of which would work at the moon. The Deep Space Network at JPL was operating at about 980, as I recall, megahertz, and was moving over to S-band. And they had the only systems that would operate at the kind of distances we needed. So our problem was we needed to operate from here to the pad, which turned out to be fairly difficult. And then from the pad to Earth orbit, then Earth orbit to translunar, and then from the Earth to the lunar surface. Then on the lunar surface, you got two guys out, you've got a guy orbiting the spacecraft, you've got people on the ground, you've got a television set or camera, you've got all these different ways, and the links all have to somehow work together to get back down to a TV screen here at Mission Control and in the general public. So what we wound up with was one of everything. We had an HF system, a VHF systems, we had UHF systems, and we had S-band systems. And ultimately, if we'd kept flying, I think we would have gotten around to just the S-band system, which was the ultimate goal. The goal was to go from the transition period of all the different frequencies to the S-band system, which would be a single unified system. At the same time, there were other transitions going on. We had the transition, if I can find where I wrote that. We had the transition from analog to digital systems. You know, everything at one time, if anybody else is this old in the room, everything at one time was done at analog. You had 2 cycle per second bandwidth telemeter channels, things like that. All the circuit designs were done in analog. One way of dealing with analog was you over-design everything and you put buffers in, and as the system degrades, you still get an adequate signal out. The other way was design it where it worked right in the first place, and then it would just degrade. And that was a lot of the Block 1 command and service module system. So let's see, there was a third integration going on, and I don't recall what it was. Okay, the television, in case you've heard that there was a very systematic approach to putting television on the spacecraft, you're wrong. There had been an experiment, I guess it was Gemini, we did the line scan thing that looked terrible. The Russians had put up television, so we tried, and it looked terrible. And somebody was talking about the giants of the space industry had decided never to be that embarrassed again. And so we worked a plan. George Miller did not want television on Apollo, so he would say no and we'd say yes, but he never told us to quit. So we kept building the communication system to handle color television. And every other month or so, I'd go with this group up to Washington, and I got to give the presentation on color television because I was youngest, and if I got fired, I was the most expendable. And so we finally decided that this time we were going to take the big guns. Werner von Braun himself was going to say that television was required for Apollo to maximize the political everything of the program. But Werner dozed off while I was giving my pitch. And I do that now. But fortunately, Sam Phillips was sitting behind him, and Sam knew the criticality of this decision because we had already installed the camera. And JSE operated no differently then than it does now. Okay, so I started working my way towards where Werner was sitting, swinging the pointer against my leg, and Sam caught what I was about to do. So he leaned forward, and when I popped the table in front of Werner and woke him up, Sam said, "Television, television." And Werner says, "Oh, yes, if I think we must go to the moon with color television, it is what the people of America have paid for," and then he dozed back off. So that is how, in his British accent, we got television on Apollo. Okay, let me have the first 2 view graphs, please. Now you see why they sent me to headquarters. These are the kind of things we were trying to do, and I've been over them a bit. Voice telemetry, we had 2 rates, ranging, tracking, up data, voice and data playback, television data, and television had to be from a command module, had to be from the lunar surface, so that brought us multiple sets of problems. And then there was a science bay in the service module that we put in at one point, and there was a science package left on the moon, so that was 2 more links. Then you had VHF voice. The reason for this is, you had airplanes around the world that were equipped for VHF recovery for military purposes and for HF. So we had to carry those because we weren't sure, we didn't know much about what we were going to do with Apollo, regardless of what these folks say. And we weren't quite sure where it was going to come down sometimes, so we had to make sure that somebody somewhere could find it. And that was the reason for the HF, for example. HF, if it bounces long enough, somebody will hear it. And the ultimate goal, of course, is to home in on that and find out where the spacecraft was. And that's why they all went down to, the astronauts all went down to Canal Zone and learned to eat rattlesnake and boa constrictor and things like that. That was their level of confidence in what we were going to do for them. Okay, so the problem, of course, the Mercury network, which was in the Gemini network, were all these stations around the world. And as I said, they had the VHF and UHF systems. Next view graphs, please. Now, this is where you're going to have to use your imagination because there were 5 view graphs in this set. Okay, pretend that's the Earth. The problem here is this is the most complex. You've got 2 astronauts. They have to be able to talk to each other, and they want to talk in duplex, so that if something goes on, you don't have one yammer-jaw that, similar to Owen's presentation, that you just can't shut them up and get a word in. And then you want to be able to communicate through the lunar module, then translate over to S-band and go to the Earth. Same time, you've got the command service module. At the time, there was no S-band frequency domain set aside for deep space communications, and that activity had to go on in parallel. And there was an international body that we never were quite sure was going to say we could do this while we were building all the equipment. And towards the end, they finally approved it, and we were able to use it. Envision the fact that when you're near Earth, and this is a command and service module, you're near Earth, you've got these communication links with the Earth. There's a lot of, the problem with communication became one of management. Everything had to be multiply switched, and then there was a big, long procedural thing you had to go through to make sure that nobody threw the wrong switch at the wrong time, because you had a very complex system of relays with backups. And the problem with any system that's very flexible is then you have to come along and constrain it later to make it work to make it work at all, let alone the way it was supposed to. So I don't recall, except for the communications between the blockhouse and the pad, I don't recall ever having a communication problem. There was a serious problem there for other reasons. Now, when we were looking at, I think it was Apollo 15 rover, first time around. I think it was Apollo 15, it became obvious the rover was going to go a little too far out. So communication packages were added to the rover itself that you could relay EVA through. And I see Joe McKenzie back there. He participated in that development. It's a Lunar Communication Relay Unit. Then it dawned on somebody you also needed television for that. So you put the camera on the front end of the rover, and then it relayed through the L crew or whatever they called it. And that gave the link then directly from the rover to Earth. So you had a communication link from the command module circling the moon to the Earth, a communication link from the lunar module sitting on the moon to the Earth, and a communication link from the rover to the moon sitting on the Earth, rover to the Earth sitting on the moon. So it was a complex system, and almost, well, I think I'll stop at that. What's the next chart, please? As I said, the frequencies we're talking about here, the S-band system for lunar module and command module, they was where as I recall, it was a 228 to 230 ratio between transmit and receive, or the other way around. This number, in the interest of accuracy, my light doesn't work yet, but that number is 2106.40625. See, some of us never forget anything. That's the way you do the space station budget, is that many decimals. The downlink was 2287.5, and that was a coherent link with the uplink. And you'll notice over here, if you do the calculations, if you care about it, they're the same ratio. And we also had an additional downlink from the command module for stored data. The antenna system was a rather complex system, and there were multiple power levels that were available. Also, the antenna, the high-gain antenna, had multiple switching so that the crew wouldn't have to bother with trying to point it. It could lock up on the Earth as it moved out. It would get to compensate for the loss of signal due to longer distance. It also would switch down and decrease the beam width, and therefore increase the gain of the antenna. So it was a rather neat transition from the Earth to the moon. Next, please. For the CSM systems, which our ultimate goal was to drop the VHF system, but and I suspect that was done with the shuttle. I went off to become a private detective and never checked back. Let's see, 5 watts was the power on those, and there were omni antennas on both spacecraft. But again, because of the fact that you had to break the command module from the service module during reentry, we had to have multiple sets of antennas there also. Next few guys, please. Then for recovery, we had high frequency system at 10.006 megacycles. We took that off in block 2, and it was a fortunate move because it left a cold plate in the Block 2 spacecraft that was unoccupied. And it occurred to somebody at one point that the lunar module had a rendezvous radar it could use to find the command and service module, but there was a problem that if you got to a safe low altitude abort with the lunar module, there was no way for the command module to come down and find the lunar module. So the question was, how could we modify the system we had, since we were going to launch Apollo 8 fairly soon? We were given 13 and a half months to develop some system. We took that cold plate, put a digital range and range rate system on it, and used some spare wires in the GNC harness to give a range and range rate capability to the voice system within the command module. So used range and range rate and the optical sight in the command module to find the lunar module. So for $15 million here, you got the equivalent of, what, the $100 million rendezvous radar and a lunar module. And a little commercial there, too. We used to have two divisions, a command module division and a lunar module division. The lunar module division wasn't as smart as the command module division. Okay, then from the moon, I get to say that since they're not here. Then from the moon, we had this separate package at 2119, and those transmitted for quite a long time when they got out to the nuclear-powered systems. And I was told I had 1 minute, so I'll quit. I'll be the only guy up here who did this on time. Any questions? Besides the fact I don't have to get fired. Is that it? I saw somebody. Is that legal?
The question is, could you tell us a little more about the scientist Hubble, after whom the Hubble Space Telescope is named? We're getting a second commercial.
Okay. Edwin Hubble was a guy who finished high school and was going to be a professional football player, and instead World War I came along and he volunteered and got shot to pieces and decided he couldn't be a football player. So he went back to college and became a lawyer. He got bored with law and he went back to college and became an astronomer. After he went into the astronomical business, he noticed that there was some motion that other people weren't reporting in with what they were seeing in photographic plates. And he came up with the idea that there was a rate at which stars were moving away from us, and that rate was a function of the distance away. And that gives rise to the term the Hubble constant. The Hubble constant was, he misestimated a little bit. For the techniques he had, he was very accurate. And that is an argument over whether he's 100% off or he's right on. But what that tells us is that the universe is indefinitely expanding. The issue then becomes, is it expanding to a point at which it will go to equilibrium and stay? Is it expanding to a point where it'll continue to expand forever? Or is it expanding to a point in which it'll stop and then collapse on itself? That's vitally important to us, since it may happen in 2 billion years. And that'll be called, you've heard of the Big Bang, that'll be called a Big Crunch. And that is the name for it, the jargon name for it. But the key is that Hubble was a guy who really discovered the fact that the universe was not a static thing, that it was not just sitting here, and that we were not one element, and the universe was that little thing we can go lay on our back in the grass and see. That in fact it just goes on and on and on. And the purpose of the Hubble Space Telescope is, number one, to better evaluate the Hubble constant, to give us a better feel for the age of the universe and what's going on with it. Other things it'll do is determine the formation of the earliest galaxies that we expect to be able to see some 15 billion years back in time. And if we can do that, we can confirm or not confirm a number of the theories of how the universe developed from the Big Bang.
Thank you very much, Doug. I think you can understand why communications is his forte. Our next speaker is Ken Cox, who is currently the chief of our Avionics Systems Division, and he will discuss the onboard guidance, navigation, and control systems of the Apollo program.
Thanks a lot, Joe. I was going to state first that I had a cataract operation less than a week ago, so you may see a one-eyed presentation here. Okay. But the doctor told me to stay away from bright lights. Oh dear. And I didn't realize this. But anyway, if I squint, there's a reason. When I went through the guidance, nav, and control from a command service module, CSM, and from a lunar module, it brought back the fact that there are a hell of a lot of acronyms that I'd forgotten. And it took a while to start picking some of them back up. I would like to say this, that I'd like to give appreciation to the fact that Norm Sears and Russ Larson from Draper Lab helped me put this presentation together. And back in the Apollo days 20 years ago, it was called MIT Instrumentation Lab. And they had a major responsibility as far as the development of the onboard guidance, nav, and control. Let me go to the first, next slide, please. Okay, what I intended to do was to religiously follow the assignment given called How Did We Get There? But I quickly decided I had enough material that I couldn't explain how we got back. Okay, and I followed your instructions, Joe. What I want to do is I've got about 7 or 8 slides just to talk off of, and I wanted to avoid giving you equations of motion or detailed descriptions of hardware, and try as I go to give you some of the human element, because it's really interesting if you were involved in a project like this, many of the things that have happened. I'll talk about the lunar landing mission phases, but because Ron Berry and some others have preceded me, I'll skip over that rather quickly, and then describe what the equipment was on the lunar module and the command module. And what I decided to do was I asked myself, well, what were some of the really significant operational and technical events that happened on the way to the moon, where I would finish my particular cycle as far as once the lunar module touched down on the moon. And I came up with 4 areas that I thought were important in the guidance, nav, and control area. One was the fact that the onboard spacecraft with the scanning telescope and the sextant had the capability to do autonomous nav. Now, as previous speakers have talked about, the ground system was the primary system, but there was the capability that if for some reason the communications gave out, was there some way to get back self-contained, and that capability was built in. The second item that I will discuss in a little bit of detail is the fact that, like Doug just mentioned, Doug Bloom, in the control area, we went through this analog to digital conversion right in the middle of the project. And we ended up that for Gemini and Mercury, the previous spacecraft, there were analog autopilots, analog feedback systems, and that's the way it started out on the Apollo program. North American was responsible for the command service module, and they had an analog SCS system, stabilization and control system. Grumman was responsible for the analog flight control system or analog autopilot for the lunar module. And we went through what we call a Block 2 exercise and decided to go with digital control systems, and it was a fairly significant decision at the time. And so what I'm going to talk today is more of the primary system as opposed to the backups. The third significant event that I'll talk about is that I went back and reviewed a lot of the work, and without a doubt, the final powered flight phase of the lunar module descent propulsion system, where we were headed toward the moon, but with the big engine on, if you will, and how that got developed was indeed a significant contribution. And I'll talk a little bit about that. And then finally, you get showed an awful lot of equipment, but how the crew, how the astronauts worked with the guidance, nav, and control system, and how that interface was developed between the man and the machine was really a challenging area, and many, many people have contributed as far as the work that went on. Okay, next chart. All right, I think I'll go through this one rather quickly. I've got the mission phases here, but most of what I'll talk about today start from, say, the translunar injection, where we actually get out of the orbit of the Earth, where the Saturn has taken us, and we're headed toward the moon. And as we head that way, in general, there were either 2 or 3 mid-course corrections that were planned, as I recall, translunar corrections. Once we get into the lunar orbit with a LOI, lunar orbit injection, which I think has been talked about also, then we're around the moon in a certain time period, and at the bottom is a picture that shows going down where once the lunar module, the LEM, and the command service module decouple, and the command service module stays in orbit around the moon, the lunar module has an injection, a slight burn, and then it coasts for a long time, and then we finally get to the final powered flight landing that I'll talk about in more detail. And that's where I'll stop as far as any comments on the guidance, nav, and control system. Now, there's an awful lot of work as far as what did we do to design the control system when you lift off from the moon for the ascent and the rendezvous that went on and so forth, and coming all the way back to Earth and re-entry and so forth, but I won't cover that area. Okay, next chart. This just tries to show what some of the major equipment was for the onboard system. In this case, we're talking about the command module, or the command service module, really. And it turns out that the optics, which gave us some of the autonomous navigation capability, consisted of a scanning telescope and a sextant. And the functions of aligning the platform, which was a three-gimbal platform, using the optics was part of the function, as well as navigation sightings. The computer, I think I heard Ron say that there were not enough memory, but when we started the project, I think we started with 24K memory, and we eventually went up to 36. And 36 was a lot of memory, right? And surely we wouldn't run out. Wrong. We went through the Black Friday, as Ron said, and cut all those elements out that had been developed and so forth. And just to show that history, we always learn, you know, we went through the same thing on the shuttle, and we ended up with 64K. So surely that would have been enough for the shuttle, and that was before we doubled the